It's my pleasure to introduce Professor Joe Graffam, Pro Vice Chancellor of Research Training and Performance Enhancement at Deakin University. And Joe will explain to us the origins of the Harrison Innovation Lecture and the Barry Jones Medal. Joe.
Thanks, Aaron. This lecture has been named in honour of James Harrison, who was the first editor of the Geelong Advertiser, and he was also one of Australia's original innovators. He invented the mechanical refrigeration process for creating ice, amongst many other achievements. Warwick likes to say that led us to cold beer, and that can never be a bad thing. The Harrison Lecture was introduced in 2014 in recognition of the long history of research-driven innovation within the Geelong region. And the 2017 Harrison Lecture will be delivered today by Professor Emma Kowal from the Alfred Deakin Institute at Deakin. Emma holds a Bachelor of Arts and Bachelor of Medicine and Bachelor of Surgery from the University of Melbourne, which she got in 2000, and also Doctor of Philosophy from the University of Melbourne in 2007. She's received the 2015 Paul Burke Award for Early Career Research, awarded by the Academy of Social Sciences Australia. She was awarded a National Health and Medical Research Council postdoctoral research fellowship in 2007 to 2012, and that was followed by an ARC Discovery Early Career Researcher Award, or a DECRA, that she recently completed. In June 2014, Emma joined Deakin University as Professor of Anthropology in the Alfred Deakin Institute for Citizenship and Globalization. She's received 21 grants and consultancies worth $4.4 million thus far. The title of Professor Kowal's message is Harrison's Gift, Frozen Life in a Melting World. Please join me in welcoming Professor Emma Kowal.
Thank you so much, Joe. And I also would like to acknowledge that the land that we're meeting on today is on the traditional lands of the Wadawurrung people, and pay my respects to elders past, present, and into the future. Here I am. And I'm here for the Alfred Deakin Institute. I'm a Professor of Anthropology there, but I'm also convener of the Science and Society Network, which is trying to bring together scientific researchers and social science and humanities researchers at Deakin University, and hopefully you'll see some aspect of social science research that is part of this network tonight. So I want to start my talk in a slightly unconventional way by telling you what I'm not going to talk about tonight. So when Joe invited me to give this lecture, I pondered what I could talk about that would most interest you. I'm an anthropologist, a cultural anthropologist, but also with a medical background. And in the last few years, my work has focused on the social, ethical, and cultural implications of genome science, of genomics, for Indigenous people. So part of that work has centred on what is now the National Centre for Indigenous Genomics, which is at the Australian National University, and I was founding deputy director. And this was set up as the first Indigenous governed genome facility in the world. Certainly it was innovative in many, many different respects. And its mission is to draw on genomic science for the benefit of Aboriginal and Torres Strait Islander people. But I'm not going to tell you any more about that. My involvement with this, though, led me to the history of the collection of biological samples and data from Indigenous people. So this is the focus of my future fellowship that I've started a few months ago. So this one image is a classic image of Indigenous research in Central Australia from an expedition in the 1930s by the Board of Anthropological Research in Adelaide, who would measure, photograph, take physiological measurements of metabolism, do scholastic tests on children, even collect crayon drawings. And these expeditions started in 1926 and went right up until the 1960s and amassed a huge amount of samples, data, that are held by the South Australian Museum. So you could have heard more about these things, but you're not going to. And all of this is because I did my due diligence in preparing for this talk and watched the YouTube recording of last year's lecture. And when I realised who James Harrison was, and Joe's alluded to this, I realised what I should talk to you about. It became perfectly clear. I'd heard about James Harrison in the course of editing a book that came out just earlier this year on something that myself and my co-editor, Joanna Radin from Yale, call cryopolitics. So cryo comes from the Greek word for frosty or cold, and so you would have heard words like cryonics, cryogenics, which I'll talk about later on, freezing whole bodies, or maybe the latest health and beauty craze, cryotherapy. Don't bother spending money on it, but unless you really want to waste your money. So cryopolitics is an academic term we coined to try and understand the consequences of freezing. So I'm sure you're asking yourself right now, how did I get from research on Indigenous people to editing a book on freezing? I'm going to wait until later in my talk to tell you, just so you can all try and guess and then see if you're right later on, just to build some suspense, a bit of a game. But in the meantime, I'll tell you what Harrison has to do with freezing, which is much easier to answer because Joe has already told you. I was going to ask for a show of hands, but you've all got ears, you've heard. This is James Harrison. Sorry, I don't have a better quality photo of him. He was a Scottish printer who migrated to Australia in 1837 at the age of 21, and, as you know, founded the Addy in 1840 in the very early days of Geelong. Wasn't really a town at all back then. He spent 27 years here in Geelong and then left for Melbourne and then London and returned just to spend the last 2 years of his life on his block at Point Henry. So he's known for two things, his publishing and journalism, firstly, and his pioneering scientific work, mostly on refrigeration. With no formal scientific education beyond a few courses of night school at the Mechanics Institute in Glasgow, he set his mind to building an ice-making machine. So this is the Harrison Sieber refrigeration machine, which became standard for many, many decades all around the world. So to understand how important this was, you need to understand that ice was an incredibly important 19th century commodity. And Norway and Sweden provided ice to Europe, and actually Boston provided ice to the colonial world, and it was the mainstay of the New England economy for the later part of much of the 19th century. And commercial ice, at the time when Harrison came to Geelong and started his research, commercial ice was very novel. The very first shipment of ice had only arrived in Sydney in 1839. Ice was terribly important to the colonial world. It was actually seriously doubted in the 19th century whether white Europeans, could thrive in the tropics. And in fact, the very first medical research institute in Australia, in Townsville, was developed in 1910 with the sole purpose of answering this question: could white people survive in the tropics? Apparently, in the end, they could. So they answered that question. So cool environments were seen as critical for Europeans, and especially white women, to inhabit Australia's north in any numbers and survive the summers of southern Australia. Ice was also a luxury item that allowed for food and drink preservation, obviously, and it facilitated the classic British colonial ritual of gin and tonic at the end of the working day, and of course, as was mentioned, cold beer. In 1854, Harrison began working on an ice-making machine at Rocky Point, and the following year he succeeded in creating and patenting an ether liquid vapour compression fridge, what he called a refrigeration machine. He went to London to develop his engineering ideas further and sold his first ice-making machines to beer makers in England for beer production in 1857, and one of these was still in operation 30 years later. And all of these wonderful tidbits are from a biography of James Harrison by Roy Lang. I didn't do the primary research here. So these machines, as I said, were really standard all around the world. So in the 1870s, back in Geelong, he took on an even bigger challenge, the export of meat from Australia to the UK. So this was another major refrigeration freezing challenge. And this is an image of a shipment of frozen meat arriving in Sydney from London. So the problem of transporting meat over long distances had occupied engineers and industrialists for quite some time with no success, and it was really seen as the barrier to opening up the Australian economy. As living standards improved in Europe over the 19th century, the ability to eat unseasonally, to have lamb at any time of year, for example, became a coveted commercial goal. So we wanted to bring Australian meat to the UK. As a commentator at the time put it, climate, seasons, plenty, scarcity and distance will all shake hands, and out of the commingling will come enough for all. I mean, of course, this is at the expense of the dispossession of Aboriginal people and eventually the ruining the Earth's environment. But at that time, this was obviously nothing that anyone was thinking about. So Harrison again took the lead in this international challenge to bring Australia's meat to Europe. And in the summer of 1872-73, organised the first ever attempt to reach London from Melbourne. And previous to that, he'd proven that frozen meat that was frozen for months was actually edible and fine when you thawed it again. And this was another major challenge for the meat trade to prove to consumers that it was okay to eat something that had been frozen for a long time. So, unfortunately for Harrison, tragedy ensued when a mechanical fault spoiled the 2 tonnes of meat on the 34th day of the voyage, and it was a massive failure that totally bankrupted him. Inferior colonial workmanship was blamed. But interestingly, the first successful attempt at exporting beef to the UK didn't come until a full 7 years later, so he really was incredible innovator, and of course his failures were necessary for later successes of others. So the example of the frozen meat trade showed us the ability of freezing to overcome space, to make things mobile, so that people could eat something that was actually only available across the other side of the world. It's quite an incredible feat. As the 20th century went on, freezing was used to transport vaccines, fruit and vegetables, and medicines around the world, building economies and saving lives by linking plenty, scarcity and distance, as the commentator said. In the 1930s, the science of cryobiology, so cold biology, developed the ability to successfully freeze cells without destroying them by adding glycerol, which paved the way for things like artificial insemination and blood and tissue banking. So now we're going to get really exciting and talk about bull semen. I'm going there, I've got to go there. The standardisation of beef as a commercial product was the result of the ability to freeze and transport bull semen. This was also incredibly important for the economy of Australia and many other places, and is actually the agricultural industry, the pastoral industry, I should say, that pioneered mobile refrigeration techniques in the 1950s. So it was the need to get not whole big ships full of tons and tons of meat, but to get small things, little glass vials of bull sperm and bull semen from farm to farm that pioneered these mobile refrigeration techniques. But along with its effect on space, being able to move things quickly from place to place, there is another aspect of freezing, and that's its ability to overcome time. So that's what I want to talk about for a little bit. So on one level, to say that freezing makes things mobile across space, but it also affects the temporal aspect, the time of things. On one level, it's a pretty banal statement, because in order to make things mobile across space, in order to be able to get your yogurt to the consumer, freezing must slow things down in time to slow down the cellular processes of decay, to slow down rot. So in order to make things move, to give you time to move things across the world, we need to slow down decay. But there's, on another scale, freezing is used for much larger temporal interventions, that is, interventions in time. Freezing salvages things that would otherwise disappear, making them persist into the future. Freezing can extend lifespans and even suspend death. To go back to the livestock example, the oldest semen believed to be in existence was from a sire named Cottonade Emmett, and it was collected in 1952 by the American Breeders' Service and used to sire offspring into the mid-1980s. Cottonade Emmett's reproductive lifespan far exceeded his actual lifespan. This brings us to perhaps the most well-known case of the temporal effects of freezing. Does anyone see this? Yes. Or read the book? Henrietta Lacks was a poor African-American woman from rural Maryland who died of cervical cancer in 1951 in Johns Hopkins University Hospital in Baltimore. A few months before she died, her cancer was surgically removed. Unbeknownst to her, cells from her cancer were used by her doctor, George Otto Gay, to create the first immortal cell line. So an immortal cell line means that the cells will never die when kept under the right conditions. And because they're cancer cells, by definition, they've lost the normal growth and death cycles of cells. And you can actually, scientists figured out how to keep these alive indefinitely in petri dishes in the lab and allow them to do all sorts of experiments and create all sorts of innovations, biotechnological innovations. The ability of scientists to freeze her cells, freeze the cell lines, allowed them to be sent anywhere around the world, and they were very widely sent. Within 3 or 4 years, they were in labs literally in many, many countries in the world. Her cells have been a crucial research tool for many decades and are used in thousands of labs and translated into huge profits for the companies that produce them. In 2010, it was estimated that 20 tonnes of her cells had been grown in laboratories around the world, and it's probably way more than 20 tonnes by now. Her family knew nothing about this until 1975 and have spent many years seeking recognition and compensation. Her story was immortalised itself in a 2010 book by the science journalist Rebecca Skloot that just was read incredibly widely, and just this year was released as a movie starring Oprah Winfrey. It's Henrietta Lacks' story, probably more than any other, that have got people around the world thinking about what it means to have parts of ourselves persist beyond the natural limits of time and space. So, having already broached the topic of bull sperm, I've warmed you up to talk about human sperm. Most people would know, perhaps vaguely, that the first test tube baby, Louise Brown, was born in 1978. Less well known is that the first successful pregnancy using frozen sperm occurred in 1953, although it wasn't announced for another 10 years because of fear of moral panic. The idea in the 50s that a human could be born from something that had been frozen was just considered like no one's going to be able to deal with that. But, what are the ethical implications? What kind of person is this going to turn out to be? I mean, similar in a way to concern in the late 19th century about frozen meat. But frozen sperm turned out to be fine as well. Soon after it was announced in 1963, the first sperm banks were set up in the US and Japan, and then rapidly in many, many other places. Sperm donors have greatly extended the natural reproductive capacities of some men, whose sperm donations might produce 12, 50, or even over 100 biological children. So we have this image at the top from a series called Generation Cryo that was on US television a couple of years ago. And all of these young people in the image have the same biological father, the same sperm donor. And the show is about them all. One of them documentary about one of them going and trying to find all the others and create kinship. So we have new types of kinship being produced through the use of reproductive technologies. In the US, mothers of children born with donor sperm have created voluntary registries where their children can find biological half-siblings. And I actually don't know if this is happening in Australia. They do this to create kinship ties, but also to avoid incest, as in many cases, the different offspring of one donor live in the same area and might even go to school together. So it's actually a bit of a problem. So in this case, freezing telescopes the normal time frame of human reproduction, allowing what would normally be many generations of descendants to crowd into one generation and have a single parent, biological parent. It also telescopes human evolution, amplifying the genetic traits concerned in certain frozen vials, in certain sperm banks. And this is actually apparently of concern to geneticists, that there might be some traits that are, and some genetic diseases that are being very unnaturally extended through the population. So now we get to the other couple of images on that slide. Freezing eggs, human oocytes, has proven much more difficult than freezing sperm. I don't know what you want to read into that, but it just is. It's only in the current decade that it's become viable after the first successful pregnancy from vitrification or flash freezing of eggs occurred in 2010. In the last 5 years, social freezing of eggs has become a major industry. I don't know if anyone's come across it, but it's quite amazing. Middle-class women are encouraged to freeze their eggs in their 30s or ideally even in their late 20s in order to achieve better success from IVF when they might get to IVF in their 40s. So all of this is about trying to make a technological solution to the problem of women in the workplace, basically. And as women of my generation know, who were brought up with the kind of promises of feminism that we could join the workforce and we could have it all, and then have found that, no, it's actually quite difficult to have it all. To have a career and have children is incredibly challenging. So this is being now, to the next generation, I suppose, or to Generation Y, it's being, and the millennials, they're being told, well, you can have it all as long as you put off childbearing until after you've made your career, probably late 30s, early 40s, and when you've had time to find the right man, because of course you're way too busy and also way too successful to have a kind of usual course of relationships. So freeze your eggs, then you'll have no regrets. Buy yourself some time. So there's incredibly wonderful imagery that you can imagine about biological clocks and wombs and eggs. So you can put work first, reduce stress. You don't have to worry about it. It's a technological facilitation for leaning in, to use this term that Sheryl Sandberg has made very famous. And interestingly, not surprisingly, Facebook and Google have subsidised, have basically are paying for female employees to freeze their eggs. So women are freezing their eggs to extend their reproductive lives and increase their chances of producing kin who will carry their legacy into the future. Freezing is used for another, more extreme form of life extension, cryonics. And I'll get to the critique of egg freezing later on, because obviously there's a lot to say there. So cryonics, this is freezing whole bodies. Has anyone not heard of this before? Oh, it's pretty well known. The birth of cryonics is usually located in Robert Ettinger's 1962 book, The Prospect of Immortality, and the movement that grew around him in the US. The first person was cryopreserved in 1967 and is still frozen. Although in the 70s there was a cryonics scandal where someone had set up an operation and who wasn't really a professional, wasn't a scientist, and he ran out of money and 9 people thawed. So after that, the industry went into a bit of decline for a while. And of course they were already dead beforehand, but yeah, it's not good. Over 250 bodies are cryopreserved at the moment in the US alone, and over 1,500 people are signed up for cryopreservation after their legal death. The process of cryopreservation illustrates this blurring of life and death that you get that's induced by freezing. So we had Henrietta Lacks's cells that come from her cancer. Are they still alive? Does that mean that she's still alive? And so we also have cryonics, and people who are cryopreserved are clearly in a state that is, well, some people see it as death, other people see it as potential life or waiting to be thawed in the future. So the process of cryopreservation actually illustrates this blurring between life and death that freezing induces. So in the US, and in Europe as well, they have cryonic volunteer squads that if you signed up, you've paid your dues all your life, and then you're in hospital and you're critically ill, you're about to die, somebody from your family, or presumably not you because you're very unwell, rings up these volunteer squads, and they come, they live in your state, they quickly make their way to the hospital, while the company, who's probably interstate, is organising a team to come and retrieve you. So the volunteers go in, and basically their main job is to convince the treating doctors that you may be dying, but you're not actually turning into a dead person. You're turning into a patient of the cryonics company. So they try and convince the doctors not to perform heroic efforts to try and keep you alive that might, break your bones, might crush your chest if they're doing CPR on you, and damage your lungs. They also don't want you to use certain medications that you might usually use in resuscitation of someone who's about to die. And then the cryonics team comes, they move in, and hopefully having convinced the doctors that they want to preserve the body as much as possible, they then transform this person from someone that's clinically dead to someone that is waiting to be thawed in the future. So it's trying to cheat death, obviously. It's trying to extend your life so you can be woken up at some time in the future. It's mostly white men involved. You might not be surprised by that. And obviously rich people. Actually, I don't know how much it costs. I haven't looked into it. It's probably not. I mean, I'm sure they have a market that they're trying to meet. And it's interesting, though, to think about it as potentially a technology for people who don't have descendants. And it's been noted that quite a few people who have been frozen don't have biological descendants. So in some ways, in the same way that women who are freezing their eggs are doing it in order to try and create biological descendants and have a career at the same time, in some ways these men who are freezing themselves are trying to create descendants that's actually themselves. They're making kin of themselves in the future. And of course, future imaginaries are incredibly important with freezing. Every time you freeze something, every time you preserve something, but particularly when you're freezing something, you're thinking about what will happen in the future. And the trust, and maybe it also explains why they're white men, because the trust that these people have in handing over their bodies, even their dead bodies, to be thawed is amazing. Their trust in who might be there in the future to thaw them. They could be harvested for organs. They could be thawed to become slaves to aliens. I mean, who knows? Who will thaw us and for what purpose? These things don't bother them, obviously. Or they're willing to take that chance, that leap. A much less kind of optimistic kind of freezing is environmental freezing. And here I'm thinking of things like frozen zoos, frozen arks, and seed banks, the Norwegian seed bank there in the bottom. So the the example we have in this top image of the frozen ark is one of many ecological preservation projects around the world that are making technological interventions in the problem of the scarcity of biological diversity, the deterioration of the environment. So the frozen ark, the top one there, their website tells us that they strive towards a world where extinction rates are sustainable and not created by man, where the beauty, splendour and practical solutions found in all species is noted and used by man for the good of mankind and for the good of all life on Earth. So the kind of gender non-neutral language aside, the Frozen Ark project is trying to preserve all the endangered species either as whole organisms if they're small enough, or preserving their gametes, sperm and eggs or embryos, so that some of them are already extinct, or many of these species may become extinct in the future, so that they will be preserved. And there are already quite a number of reanimation projects that have happened with amphibians in particular, that try and use genetic material or frozen organisms and bring them back to life, or bring cells back to life. So this again is in some ways it's a hopeful project that things can be brought back to life, but of course also very incredibly pessimistic that we need to keep the world's biological diversity frozen because it's not safe on Earth itself. One really interesting aspect of the frozen arks and frozen zoo projects is that in species conservation, the number of live animals that need to be maintained is actually, in some cases, they take into account how many species are frozen. So the frozen population, the population of gametes and organisms that it might be in a frozen zoo, is kind of coterminous with actual living animals when some species, when a calculation is made about how many of these should be kept alive, how much resources should we be putting in to preserving animals in habitats. Similarly, the Svalbard frozen seed bank on the remote Norwegian island of Spitsbergen has a mission to provide a safety net against accidental loss of diversity in traditional gene banks. And they describe that war, political instability and natural disasters have all destroyed the seed banks of the Philippines and Iraq and Afghanistan, and many others in the future may be at risk. So this seed bank has 1 million seed samples. About at least more than a third of the world's banked seed diversity is backed up in this particular seed bank, and it's seen as a very safe place. Obviously, it's somewhere that's usually frozen, but just over a year ago, you may have heard that the seed bank flooded. Water encroached 15 metres into the entrance tunnel, and the construction of it has to now be rethought in the face of climate change. So all of these things that I've talked about, frozen arks, seed banking projects, and even cryonics itself, and definitely egg freezing, are technological fixes for social problems. In this case, the problem of carbon pollution from our reliance on fossil fuels and from the ideal of endless economic growth. And in the case of egg freezing, the problem of workplaces that do not take into account the demands of raising families. And this is something that we should really think about, that James Harrison wouldn't have thought about at the time. He couldn't have known the kinds of consequences that have come from freezing. So here we have frozen ice cores, just to get a double freezing sense here. And ice cores have been incredibly important for understanding changes in climate over time and really generating a lot of the evidence around climate change. And ice cores have their roots also in the late 50s. A lot of these technologies really, they have their roots in the 19th century, but really came to fruition in the mid-20th century. At the height of the Cold War, a team of scientists who were participating in the International Geophysical Year travelled to Arctic and Antarctic glaciers. And this was the beginning of a deep an effort to study the deep history of climate change by looking at things buried in the snow and concealed in deep layers of ice. So these ice cores became dense, that they turned these dense frozen waters of glaciers into archives of the atmosphere, providing evidence of recent and significant spikes in greenhouse gases. Millennia were recovered from these cylinders, and the bubbles of ice held a frozen record of past seasons. So now, in the 21st century, 17 kilometres worth of ice cores are stored in freezers at the US National Ice Core Laboratory in Denver, where this image is from, which boasts one of the largest sub-zero experimental facilities in the world. Freezing ice cores to study climate change is obviously a practice saturated with ironies. The ability to preserve samples of glacial ice requires energy-intensive forms of preservation in order to demonstrate how fossil fuel-obsessed capitalist societies have contributed to climate change. And yet, as the planet warms, naturally occurring ice has come to be understood as a scarce resource. Already 5 years ago, NASA reported that the floating cap of sea ice in the Arctic melted to an extent less than half of what it was in 1979. And as we know, since in the last 5 years, the melting of the polar ice caps has only accelerated. We are all experiencing the warmer climate, with each year breaking more temperature records, more extreme weather events, and more heatwave deaths around the world. But too many of us respond by simply cranking up the aircon. In our warmer cities, more and more people are spending the warmer months in a bubble of coolness. The Australian Refrigeration Association reports that 22% of electricity usage in Australia is on refrigeration and air conditioning, and that's set to rise to 40% by 2050 without if we don't take any action. Our inability to face the changing climate is leading us into the warm future ever more quickly. Here, cooling is a means of acceleration, of speeding up time, of actually, being in a negative cycle which will make climate change happen more quickly. But I want to turn, in the last part of my talk, back to the temporal dynamic I've explored in different ways throughout this lecture, freezing as a means to slow things down and cheat time. So freezing as a mechanism of salvage, of saving things, has particularly affected Indigenous people around the world. So this is where, if you were guessing, you can now see if you were right about what freezing possibly has to do with my kind of main part of my work. Throughout the 19th and early 20th century, Indigenous people were seen by scientists as portals onto the human past, an evolutionary time machine. So Indigenous people were seen as Stone Age people and as kind of stuck in a lower stage of human evolution. And by studying them, we would understand the past of European civilization. This perspective of Aboriginal people as human time machines animated the earliest anthropological efforts to document and salvage the social practices, cultural artefacts and languages of such groups. So the term salvage anthropology is well known. In a mid-20th century iteration of this interest, Indigenous people came to be valued by a range of scientists who sought to salvage their blood. Assumptions about the isolation of these populations allowed them to be cast as natural laboratories for the study of unique signatures in their bodies and genetic mutations that have thought to have been accumulated through millennia of living in a state of adaptive equilibrium. They are thought to be more in tune with their environment biologically. With new research priorities and forms of molecular analysis, so as the technology changed in the lab, this blood became a precious and polyvalent biomedical resource. Concern about the so-called disappearance of Indigenous cultures in the face of modernity allowed this project of salvage to be cast as especially urgent. So it was seen in this period in the 20th century, not that Indigenous people would die out, that was more of a 19th century belief, but that assimilation would mean that these genetic somatic signatures could no longer be captured unless they were straight away recorded and frozen. Anthropologists, human geneticists and epidemiologists anticipated that such blood of Indigenous people, if properly preserved at low temperatures, could reveal many facets of human evolution and human variation, even after the societies they were collected from had disintegrated, and that these samples could continue to yield insights as yet unknown future technologies emerged. Through the eyes of these scientists, Indigenous people were understood to be both fundamental to understanding human history and also exceptional. It was their apparent lack of social and cultural change that made them essentially and uniquely biological human. A crucial episode in the 20th century effort to freeze this precious resource was called the International Biological Program. And it was a large-scale effort which really drew from the success of the International Geophysical Year to take stock of the biosphere, and it ran from 1964 to 1974. And Australia was an active participant in this international effort, with 7,000 samples collected from over 50 communities in the top half of Australia. And this is where we come back to my work. So this is a picture of Bob Kirk with an unnamed Aboriginal man in Pineapple Bore in the remote Western Australia. And the guy on the left is Robert Kirk, who was a British-Australian geneticist who took part in the International Biological Program. He was at University of WA initially and then moved to the Australian National University in 1967. And he collected these thousands of samples from Aboriginal people in Australia and came back and analysed them in his starch gel electrophoresis state-of-the-art innovative laboratory in the late 60s and into the 70s. So it was this sample collection, and this is a box of samples looking from the top from a particular Aboriginal community, that formed the basis of the National Centre for Indigenous Genomics. So these samples were used through the 60s, 70s, 80s, into the 90s, and in the 90s the sample was closed the collection was closed to scientific research because of concerns about ethics, and then I was working with the ANU in a consultant capacity from late 2010 to try and help them figure out what was to be done with these samples, which of course involved finding out what Aboriginal people wanted to see done, both Aboriginal leaders through in a consultative capacity and communities and descendants of the people who the blood was taken from. And that's an ongoing project which I encourage you to have a look at on the internet. And this is what I'll just finish with these two slides. This is an image from WA where in the Warburton Ranges where blood is being taken, and you can see, if you look very hard, somewhere in this image is where the technology that makes the blood mobile and means that it still exists today. And that's this little thing here, a thermos for transporting the frozen blood samples back to the Metropolitan Centre of Canberra. So I want to leave you with this image of this freezer as a time machine, which has meant that samples still exist in Canberra today, and Aboriginal people are having the National Centre for Indigenous Genomics knock on their door and ask them what they should be doing with these samples, all because of freezing, all because of James Harrison. So I will leave my acknowledgements up there, and thank you very much for listening.
I've just noticed an image up there, and it's probably a good advertisement of why we should maybe not be freezing people. Because in a couple of hundred years, thawing that out could really freak some really important people out. Anyway, thanks again, Emma. I'm sure if James Harrison was here, he'd be extremely impressed by that wonderful lecture. He'd be sitting back reflecting on what a profound and diverse effect cooling has had on us individually, on the planet, and I'd hope he'd raise a cold, commercially refrigerated beer in your honour. And no doubt this event will be covered by his newspaper, the Addy. So continuing on, now it's time for us to make the award for this year's Barry Jones Medal, and I'd like to welcome Professor Joe Graffam to the microphone.
Thanks, Aaron. This medal honours an individual deemed to have a significant and sustained contribution to research and innovation excellence in the Geelong region. It is named after Australia's living treasure, the Honourable Barry Jones, AC, who is one of the great champions for research and innovation in Australia, and it's a privilege for us to have him here with us today. This year, the Barry Jones Medal is awarded to Mr. John Crewe. John Crewe graduated with a Bachelor of Engineering in 1969 from the University of New South Wales. He worked at the Ford Assembly plant at Broadmeadows until 1983, when he was appointed plant manager in Brisbane. In '87, he returned to Broadmeadows as plant manager and then spent time in the United States, finally coming back to Australia in 1993 as plant manager of the Geelong stamping plant. That's relevant to the story a bit later. In '96, he was promoted to Vice President Manufacturing, Ford Australia. As far as we're concerned, through the formative years of Deakin's then new Faculty of Science and Technology, John Crewe was a creative and innovative thinker who supported plans to invigorate university education and the manufacturing industry in Geelong. With John's support, Deakin formed a university industry partnership with Ford, and at that point John was appointed as an adjunct professor in engineering at Deakin, and that was 1996. Through John, Deakin University became part of the worldwide relationship that Ford has with industries in many countries. The sharing of information and expertise that followed was consistent with the vision that John had for education and research. He saw a challenge in taking what he called the black art of the stamping process and grounding that process in evidence-based scientific principles. Up until then, it was largely artisan-based information that had been handed on generation to generation, and there was very little publication of research findings in relation to this. So much of the attention then that John gave was to education and research, and at trade qualification level, he supported development and inclusion of sheet metal forming and joining material into trade courses being provided to Ford apprentices by the Gordon TAFE. He also at undergraduate level funded the development by Deakin University of 2 units, one in sheet metal forming and the other in sheet metal joining. They were included in Deakin's Bachelor of Engineering. To put science into the stamping process, John saw that there was a critical need to collaborate with universities. To enable this, he brought together Deakin University and the Australian National University with the aim of establishing a collaborative automotive research and development program. Anybody who's familiar with Deakin's history is starting to see these connections, I'm sure. The process for this was formalized in 1997 with the establishment of what became a very successful STAMP program, STAMP being an acronym for stamping technologies for automotive manufacturing process. That project brought academics and research students into the stamping plant to do their applied research. Over time, that integrated collaborative approach has become part of the local DNA. The STAMP program operated from 1997 to 2013. In that time, 16 PhD and 24 Master by Research students graduated from the program. The STAMP program received substantial funding from the Ford Motor Company through various sources, as well as through several ARC linkage program grants. The stamp program and a sister program established in 1999, the Powertrain Division at Geelong Manufacturing Plant, have provided the foundation for the long-term relationship which Ford Motor Company and Deakin University continue to actively support today. These programs were also instrumental in the establishment and continuing development of what is currently called the Geelong Technology Precinct, and is likely to have a new name in the near future, which focuses on economic futures. This is significant, substantial, and sustained contribution to innovation in education, research, and industry in Geelong. And for this, Mr. John Crewe is awarded the 2017 Barry Jones Medal.
I'd like now to call on the Honourable Barry Jones to make the award of the Barry Jones Medal to Miss Marina Crassi. Marina will be accepting the award on behalf of Mr. Crewe, who cannot be with us today due to out-of-state commitments.
Just going to help.
Here it is.
We didn't forget to bring
Pretty big medal. Yeah. Oh, that's right. Yes, that's right. Yes, you can't just slip it in your pocket. You've got strong arms.
I do, I'm okay.
Well, there you are. I'm delighted to be here to present the award. Of course, I'm sorry that John isn't here, but you'll do it admirably. I can't help thinking that this time last year, this is where I had a very spectacular fall at a tram stop. I mean, I'm keen on public transport, but you've got to be careful. And the result was that I looked like something from a horror movie by the time I got back from the hospital. So rather than have people shocked, the process was postponed at very short notice down here at Geelong. I'm very grateful, of course, once more to have the opportunity to come down, particularly privileged and pleased to hear Emma's extraordinarily interesting lecture. And I'm glad to see that the tradition of innovation, so important with James Harrison, has been continued and is important, and that Deakin University is absolutely central to it. And as you know, Geelong, well, I don't need to tell you that Geelong passing through such a significant period of transformation, but Deakin will continue to be central to that, and that you have so many institutions of outstanding quality in and around Geelong. And so John's award, which I'm actually going to hand over to you in a moment, is a very significant, it looks back to the history of a great industrial operation which was here, then the relationship that it developed with training with the university, and it means that the kind of skills are transferable, and those skills will continue to be of tremendous importance in and around the Geelong region, and indeed not the state but also the national economy as well. So thank you very much for having the opportunity to hand over the medal, and in this handsome display, and congratulations to John.
I will take an opportunity just to say a few words on behalf of this award for John there. So first of all, thank you. It is an honour to accept this award on behalf of John Crewe. So the relationship between Ford and Deakin, as Joe mentioned earlier on, was initiated by John, and it was his vision and his leadership that led to the merging and working between industry and academia. And it was in the field of metal stamping, where with very traditional apprenticeship trade base, that he demonstrated the benefits of applying an engineering science model to it there. The partnership started with actually having master's students working with the technical teams within Ford, and expanding this to Deakin working on the global with many research projects coming through. And this relationship has continued and grown over 20 years. And I'll touch on, I started as a graduate with Ford, working underneath John, and over these 20 years I've maintained this relationship as I've travelled globally on behalf of Ford with Deakin and with the other universities. So Ford has continued expanding its relationships with universities to broader universities around Australia, but by far Deakin continues to be the most significant relationship that he does have. When I did start with Ford as a young graduate engineer, John was the executive plant manager that I worked underneath his organisation, and I learnt quickly how fortunate I was actually to have the exposure to his leadership so early in my career. And his approach was very much about mutual benefit, two-way partnerships, and Ford benefits so much from the access to the research and the scientific approach to problem resolution. So as much as we gained from the academic and from Deakin University, from Ford, we were also able to give through from there as well. And part of this as well was with the university, especially students, which is a challenge I know as we're going through innovation, and that is giving them access to real life industry problems and giving them an opportunity to resolve problems and to actually prove their research. And I think that that's part of the collaboration that was going through. So it was through John's vision and leadership, as was mentioned, that this was established, and I really am pleased, very genuinely, that he has been recognised for this award. It has continued on and it's just grown and expanded further, and many people throughout Ford and through the academic world will know how John Crewe was the one that initiated. So thank you very much to both Barry and to Joe for that award, and we'll look forward to forwarding it through to John. Thank you.
Thank you. Ladies and gentlemen, that concludes the 2017 Harrison Innovation Lecture and Barry Jones Medal Award. We'd like to invite you to stay around for some refreshments, and we look forward to seeing you all next year. Thank you.